today from reputation and recommendation systems to social choice. How many people have seen some social choice before? Okay. So maybe I should start with, I'm going to start with an introduction. It's going to be, I think the first two lectures are going to be more basic social choice, but each time in each lecture I'm going to have some new results which are more on the boundary of research. So the basic problem in social choice is to make a decision. And the situation that we're going to look at, the classical situation in social choice is that you're given n voters, you're given m candidates. You can think of these candidates as alternatives. They are often called alternatives. And then what each voter gives you is a strict ranking of all the candidates. Okay. So each voter gives you, and so in general you can imagine each voter giving you a partial ranking. All the results that I'm going to talk about apply for partial rankings. So I'm going to just assume that each voter gives you a strict ranking. So for example, a partial ranking would be each voter could list their favorite candidate and nobody else, right? So that would be a partial ranking. The results will also apply for partial rankings. So I'm going to just pretend everyone gave you a strict ranking. Okay. So voter I gives you a ranking or a permutation sigma I of all the alternatives. Okay. So that's voter I. And then there's a social choice function. So that's where the name social choice comes from, which takes all these rankings and produces either a new ranking or just a single winner. Okay. So social choice function F, okay, and there are two alternatives. One is that F takes all the rankings and produces another ranking sigma, which is a ranking on all the alternatives. Or you could imagine that F just produces a single winner. Okay. So it's a very simple classical setting. We vote in elections all the time. Like I said, it's not that important. All the results I'm going to mention are going to work for partial rankings, so or just where you just give one or two winners. So I think this is basically all of elections. And so the typical rule that's used in most elections is majority rule. Whoever gets the most first place votes wins. But there are other ways of sort of doing these elections. You're going to see some of those votes, some of those ways a little bit later. But I want to start with, I'm going to first start with something which is very simple. I'm going to look at this situation. And I'm going to try to understand what does it take to get people to report their rankings truthfully. Okay. Does it make sense? Okay. So we would like to, we're going to choose a single winner. We want an election in which people are going to report their truthful rankings. Okay. So basically we want a rule F, which is strategy proof. So what does that mean? So we'll say F is strategy proof. So I'm in this case now. Okay. F is strategy proof if if no voter can ever be better off So first of all, no voter can ever be better off in any situation whatsoever by misrepresenting her rankings. And second, there exists a scenario where misreporting is leaves the voter so the formal definition is a little bit more complex, okay? And I don't want to give the full formal definition of strategy proofness. And I also know that it's hard to read, so I'm going to read it again. Even though I won't give the full formal definition, I'll explain what's missing from the full formal definition. So if a strategy proof, first of all, no voter can ever be better off by misreporting her rankings. No matter what anyone else is voting, okay? No matter what, you fix an arbitrary ranking for everybody else, okay? And then you fix an arbitrary correct true ranking for the voter, her real ranking. Okay? By misreporting a ranking, she cannot make someone win who's higher up in a ranking than whoever was winning before. Okay? And there exists, and for any misreporting that she does, there exists some set of votes which others could have cast where she would be worse off. Okay? So the first one is sort of for all possible sigma 2, sigma 3, sigma n, and for any true sigma 1, the voter can't be better off by changing sigma 1 and misreporting it. And for any change that she would make to sigma 1, there's some sigma 2, sigma n where she would be worse off. Okay? Does that make sense? So this is strategy proofness. It's also called truthfulness. Yes? No, not necessarily. This does not imply that a single voter cannot influence the outcome. Because it just means that a single voter cannot influence the outcome by misreporting. Right. So there are lots of situations where. So let's think of the simplest example of strategy proofness, which happens in an auction. So imagine that you are selling, let's say something. Imagine I'm selling this piece of chalk, right? And I can ask everyone how much are they willing to pay, and I'm going to give it to the highest bidder. In that particular case, I could imagine a rule where the highest bidder gets charged what they bid, and that's not strategy proof, because the highest bidder would want to reduce their bid. Okay? Or I could give it to the person who bids the highest, charge them the second highest price, and that's strategy proof, because the highest bidder cannot raise their bid and benefit, cannot decrease their bid by benefit, but if they decrease it all the way below the second bid, they're going to lose. So in this particular case, it's truthful, but clearly a single voter can influence the outcome. Right? The highest voter can influence the outcome. So it's just that you cannot influence the outcome by lying in a way that helps you. Okay? And there are many, many situations where you do get strategy proofness. Right? In fact, you're going to see situations where we will get strategy proofness today. Right? So right now we're just talking about the winner.
So in this definition right now, it's just that if I don't rank my preferred guys, then up and someone says, oh, I cannot make it go higher up with what it is. That's what's better about this case.
Yes, yes. Okay. But no, sorry, but what people are submitting is a full ranking. So it means that maybe I'll report my preferred guy the winner, but maybe I'll report the person who's winning to be much lower and influence that person. So that you can do other kinds of manipulation. So the space of manipulation is very rich because you're still submitting a full ranking. It's just the state of the winner is just one single person. Okay? And the results that I'm going to describe are going to hold even if you wanted to choose a full ranking. Okay? But I'm going to just describe it for the single winner. I'm going to start with this theorem because this theorem is a little bit less well known. So since like some hands went up when people say social choice, I'm assuming that the first thing that people see in social choice is Arrow's impossibility theorem. This one is actually even more interesting, so I'm going to start with that. I'm going to give a proof of this, and I'm going to just mention Arrow's impossibility theorem, but not prove it. Okay. So, yeah. I'm going to prove that this kind of, sorry? No, so the question is this strategy proof? We don't know because we haven't defined what F is. Under some situations. There definitely exists strategy proof. Can someone think of a strategy proof rule? Sorry? No, for this setting. So the answer was the second option, but for this setting, can someone think of a strategy proof rule? So majority on the first is not strategy proof. Okay. Because imagine that so majority on the first is not strategy proof because, so majority is not well defined here. So let's call it plurality. Sorry, the reason I'm hesitating is because majority implies that a majority of the people want something. It's not a well defined rule here because there may be no one who gets a majority. So the rule is called plurality, which is the person who gets the most votes, most first place votes wins. So imagine that my best place candidate is losing anyway. Okay? But the person who's currently winning is someone I hate. So I can vote for my second person and maybe make my second person win. Okay? So plurality is not strategy proof. There's something simpler than plurality, which is strategy proof. You are better off. So imagine that imagine the following situation where a lot of people are voting for, 3 people are voting for A, okay? And let's say 3 people are voting for B, okay? And let's say my ranking is C, B, A. This is my ranking. So I'm looking at how other people have voted. Yeah, say by, I should really report C. I should really report this ranking because C is my preferred candidate. But if I report B, I can make B win as opposed to A, who I hate. Okay? So plurality is not strategy proof. Right? In fact, the theorem that we're going to show today is going to see today will directly show that plurality is not strategy proof also. But there's an even simpler rule which is strategy proof. Yes? Go ahead. Now, so that suggestion is to do single transferable vote or rank choice voting. That's the suggestion. Rank choice voting says look at the first person, whoever gets the most first person votes, right? Whoever gets the least first person votes, kick that person out, and then rinse and repeat. Okay? That's nothing that, I think this is like too sophisticated an audience to come up with a strategy proof rule. And also like too democratically inclined. Yes, anyone else? Yes, go ahead. It's a full information game, so it doesn't matter. The question is, are they submitting their rankings simultaneously? And again, without getting deep into game theory, there are 2 kinds of game theoretic situations. One where you have information asymmetry, and one which is a full information setting. So here we assume that everybody knows what everyone else is doing. Yes? So the question is, does every voter have some utility? No, they just know that they like this more than this more than this. They're a single winner, so the utility is to get the highest person in there. Okay. Anyone else about the strategy proof? Yes? Yeah. Yeah. So the suggestion is that you could assign a position to each, a weight to each position in the rank, sum them up, take the highest person. That's not strategy proof. There's a class of rules called position scoring rules. It's a beautiful and very useful class of rules. Almost a lot of elections work like that. Position scoring is where you apply a weight to every position and you just sum them up, and whoever gets the most score wins. In the specific situation, if you assign weights which are m minus 1, m minus 2, or let's say down to 0, then this is called the Borda scoring rule. And this is equivalent to just saying, just for every candidate measuring how many candidates it beats in every election. Okay? And it's not strategy proof. Okay? Even simpler. Okay? Yes? Dictatorship is strategy proof. You just pick a random guy, okay? Since Professor Manjunath is an organizer, he's a dictator, he chooses the winner and that's it. Okay? That's strategy proof. He'll never lie. Anybody else can lie all they want if I'm going to help them. Okay? It can hurt them. It can't hurt them either, right? So dictatorship is like weakly strategy proof, where lying doesn't help anyone, but there are people for whom lying cannot hurt them because they're not dictator anyway. So we need to change dictatorship just slightly. Any suggestions on how you could change dictatorship just slightly? Make random dictatorship. You pick a random person as a dictator, that's strategy proof. Okay? But dictatorship is also strategy proof if you can ignore the second part, which is more of a technicality. Okay? The question is, are there rules which are not dictatorship which are strategy proof? Okay? And that's the subject of this theorem. It's a famous theorem by Gibbard and Satterthwaite. I don't want to give the statement of the theorem first because I want you to be surprised when you see the statement. Or maybe I will give the statement of the theorem. The statement of the, is there any other property that you would like? So other than strategy proofness, is there any other property you would like these things to satisfy? Yes? Sorry? Yeah, I mean dictatorship doesn't, so the question is, would we like something other than dictatorship? Yes, we would like something other than dictatorship. Yeah, it would be good to have some kind of monotonicity, right? What's the simplest form of monotonicity that you would like? Even simpler, even simpler. Even simpler. So the answer, the thing was that, so so the monotonicity conditions that you're suggesting are very strong. Even weaker monotonicity. What's the weakest monotonicity condition that you can think of? Even weaker. So these are like very strong conditions. Like the weakest monotonicity condition that you could think of. Yeah, that is going to be, yeah, so the claim is that if I raise a voter, his rank should remain at the same level. That's going to be a consequence, but we don't want to make that as an assumption. Yeah? Because I want the theorem to be as strong as possible. Okay, let's say unanimity, which is that if everyone ranks the same voter as number 1, that voter should win. Okay? Does that make sense? That's the monotonicity condition we want. So you want two conditions, unanimity and monotonicity. No, sorry, so unanimity and strategy proofness. Yes? Yeah. Yeah. So the question is, why are we concerned with a single voter? Why not with a coalition? Okay. So that would be a weaker statement. And the reason that, so that's a strong, so what you're describing, by saying that a coalition of voters cannot misrepresent, right? That would be a stronger algorithmic assumption. But for impossibility results, that's a weaker assumption. Does that make sense? Because you're going to prove an impossibility result. For an impossibility result, this is going to be a stronger impossibility result. Yeah. So there's a notion of something called the core, which says that no coalition can misrepresent, right? That's a very hard thing to obtain in these elections. Okay. So the theorem that I'm going to talk about is one of the most beautiful theorems in social choice. I actually find it to be stronger than Arrow's impossibility theorem. It's by Gibbard and Satterthwaite. We're going to see a simple proof by Benoit. And the theorem says that if F satisfies is strategy proofness, and unanimity, then F is a dictatorship, right? And I don't know if any is like stronger indictment of democracy than this, okay? So you're going to choose a single winner if you want it to be strategy proof and unanimous. Like unanimity is about this weakest condition that you would want on a voting rule. Yeah? And if you also want it to be in addition to unanimity, without which a voting rule is not really a voting rule, then, and you want strategy proofness, then the only thing that works is a dictatorship. There's a single person, whoever that person chooses as the winner is going to win, and doesn't matter who anyone else chooses. You don't care about what anybody else is doing, yeah. Yeah. Okay. And this is true for weak strategy proofness, by the way. So I think maybe you don't even need this here. Yeah. Sorry? Yeah. No, if everyone votes for the same person, the question is, well, what is unanimity and dictatorship, how do they interact? Well, if everyone is voting for the same person, the dictator is also voting for the same person, and therefore the dictatorship. No matter what anyone else is voting, the dictator wins. So everyone may, or if everyone agrees with the dictator, then great, it's unanimous. If anyone disagrees with the dictator, then the dictator wins. Yeah, if you remove unanimity, then everything is good. If you remove unanimity, pick an arbitrary person, arbitrary alternative, because we're not even requiring isomorphism here, right? We're not even requiring it to be independent of relabeling. Pick an arbitrary person, pick a random person. Okay. So without unanimity, a voting rule is not really a voting rule. If everyone wants something to happen and that's not happening, then it's not really a voting rule. Yeah. So that's the theorem that we're going to see, either a full proof or a proof sketch, depending on how we do on time. Yes? No, sorry. No, I don't. No. No, so the question is, do we get unanimity for free because it's a dictatorship? No, I'm not saying it's a dictatorship. It's a conditional statement, right? If it is strategy proof and unanimous, then it's a dictatorship. Yeah, if it's a dictatorship, it satisfies unanimity. Dictatorship definitely satisfies unanimity because the top person's thing is going to win. Yeah. I don't understand. No. If F is a dictatorship, it satisfies unanimity. No, dictatorship just says that what I say wins. It doesn't matter whether what I say is true or not. I may be a dictator and I like pizza, but I may say I like burger, and then burger wins. So the fact that a dictatorship dictatorship satisfies unanimity has nothing to do with strategy proofness. It doesn't matter how everyone votes. If it's a dictatorship, yeah, that's not dictatorship. No, but then that's not unanimous because then he chose B. So if the dictatorship is unanimous without worrying about strategy proofness. Dictatorship implies unanimity. Okay. What's surprising is that with strategy proofness, unanimity implies dictatorship. No, dictatorship, when you do things like dictatorship and unanimity, you cannot look inside someone's brain and see what they're saying. Dictatorship just says that whatever the dictator ranks 1 wins. It doesn't have anything to do with what the dictator actually wants. No, it doesn't have to be a random person. Sorry, it could be a random person, but it doesn't have to be. So dictatorship is just where like there's one person, whatever that person says goes. No, I think we should move on. I'll take that offline. Okay. So, so we're going to see a simple proof of this, okay, at least a proof sketch. Okay. And then I'm going to see ways in which you can go past this very strong result. Okay. It sounds like a very strong result, but then we'll see some so it sounds like a very strong indictment of democracy in general, but we'll see lots of examples where you can actually get very strong positive results as well. Okay. And we'll examine why that happened. What's the difference between the two settings that you can get such strong positive results in the face of such strong impossibility results. So the first thing that we're going to do is we're going to have this factoid. Okay. This is going to just run through. So I'm going to just write this factoid, then I'm going to erase everything, and then start with the proof. Okay. And this fact has to do with something which came from the audience. I forget where it came from. This fact says that suppose A is the winner. Okay. Suppose A is the winner with the current rankings. Okay. And now suppose one voter raises one candidate X in its rankings. Okay. For simplicity, for now, let's stick to deterministic rules. So suppose A is the winner with the current rankings, and one voter raises X in its rankings. Then the new winner. Can anyone guess who the new winner should be? Either A or X. And so this is a fact that follows from strategy proofness. Okay. So if A is the winner with the current rankings and you raise voter X in its rankings, then the new winner is going to be either A or X. Okay. And so the way this follows from strategy proofness is suppose the new winner becomes Z, some other guy Z. Okay. Then this voter, if the voter prefers Z over A, then the voter will falsely increase X. Okay. Whereas if the voter prefers A over Z, then the voter can falsely reduce X. Okay. So if you want strategy proofness, then you get this factoid for free, okay, which is a very desirable fact. So the question is, it's not quite clear. Is the statement not clear or the proof not clear? Yeah. Okay. So let's assume that this does happen. Okay. So there are two rankings. Okay. So there are two rankings. Let's not worry about how everyone else is voting. Let's just worry about this one voter. Okay. And let's not worry about what else is happening for this voter. Let's just worry about the position of X. Okay. With this situation, A wins. And let's say with this situation, the only thing you change is, let's say, the position of X. Let's say you raise X. So X from number 3 goes to number 2. Okay. And let's say now Z wins. Okay. Now let's focus on voter number 1. Okay. And let's say Z is not equal to X and Z is not equal to A. Okay. So somebody other than X and A wins. Now the first voter either prefers A or Z. if the first voter prefers A, and this happens to be the true ranking of A, then of the first voter, then the first voter will instead report that. And if the first voter prefers Z, and this happens to be the true ranking of the first voter, then the first voter will instead report this. Okay. So all this is saying is that if a voter raises X in his rankings, then it can make, maybe it can make X win. Does that make sense? But it cannot make someone else win. Now, if Z is X, then there's no contradiction. Because if the voter likes A more, then in any case A is going to be high, maybe A is higher up here. Okay. So this fact is something that we're going to use repeatedly. That if I raise someone in my rankings, I can maybe make that person win, or maybe the person who's currently winning will keep winning, but nobody else will win. And then of course you can use it, we're going to use it again and again and again. Instead of moving it up by one position, we can move it by 2 positions, 3 positions. Instead of one person moving, now many people can move it up. Yeah, go ahead.
One voter raises the ranking of X by falsely representing, falsely reporting that ranking.
Sorry, what's the question again?
So the one voter raises the ranking of X by falsely reporting the ranking.
So, okay, so the question is one voter. So in this fact, this is a fact about F. Maybe I'm not understanding the question. So I'm not, that sounded like a statement, not a question, so I don't quite know how to answer it.
Initially, the A was the winner.
Initially A is the winner.
And it was the top of the rankings by the top of the ranking reported by the voter.
No, we're not assuming that. Okay. We're just saying that A is the winner with the current rankings. It may be on the top, maybe on the bottom, wherever it is. And one voter raises X in its rankings, and the new winner is going to be either A or X, as long as F is strategy proof. Okay? So we already assume that F is strategy proof. We already assume it satisfies unanimity, and therefore, and so this fact follows from F being strategy proof. Okay? Should I go ahead? So with this, then it's a 3-step proof. Some of the steps I might skip. Okay? The third step I think I'll skip. So the first step is to have a pivotal voter, is the notion of a pivotal voter. Okay? So let's pick a specific candidate B. Doesn't matter which candidate. We're going to show that there's going to be a pivotal voter. Okay? I'm going to assume, without loss of generality, that my voters are numbered from 1 to n. Okay? I already assumed that. I'm going to assume that I'm going to fix this ordering of the voters, 1, 2, 3 up to n. Okay? Sorry, go ahead. No, I'm going to define it. So the question is, what's the pivotal voter? I'm going to define pivotal voter. So this is going to be the first part of the proof. Okay? So initially, let's just think through like a simple thought exercise, okay? Which I'm hoping not to prove, but I will if there's interest. Okay? Let's sort of look at a ranking where B is last in everyone's order. Okay? Any ranking in which B is last in everyone's order. Okay? Now, in this ranking, is it clear that B should not win? Okay. So as it turns out, it's relatively easy to show that if B is the last in everyone's ranking, then whoever wins, B should not win. Okay? And so maybe it's instructive to see the proof of this, okay? Because it sounds like a very obvious result, but this also sounds like something which is very counterintuitive. So maybe it's worth proving this. Okay? So let's say in this case, I'm going to prove this by contradiction. So let's say B wins. Okay. This will also follow from strategy proof. So this is so let's say B wins in this case. Okay? Now let's pick anyone else let's pick any other voter, any other candidate A. Okay? And gradually everyone starts to raise A in their rankings. Doesn't matter by what sequence of steps they do it. Okay? Like at every step you pick an arbitrary voter, you may ask that arbitrary voter to raise A in his rankings if it's not already at the top. Okay? You keep doing it. At some point they will get to the top. Okay? When A is at the top, what do we know? A must win by unanimity. So there must have been some point at which A wasn't winning before because B was winning earlier, and A starts to win. Nobody else can win by that fact. Okay? As you're raising A, either B will keep winning or A will win. So there will be some point where A wasn't winning and now A wins. Okay? So let's say this is that point where with this just before A was not winning, and if this voter raises A by 1, then A wins. Okay? But for this voter, A was ranked above B. So this voter will then, even though A was truly here, this voter would misreport A as being higher to make A win, right? Because A is above B, so this voter would rather have A win. Okay? So this can't be strategy proof. Okay? So this is like the good side of strategy proofness, right? Because if everybody's last choice is winning, then somebody is going to be misreport what's happening to make it more move it more towards unanimity. Okay? Does this make sense? Okay. So in this particular case, B wins. B does not win, sorry. So if B is at the end of everyone's votes, then B does not win. Okay? So it's not a very strong result. It's just like B is not at the end of everyone's votes, so B does. Okay? So then what we'll do is we'll gradually, yeah. No, it cannot switch to anyone else because of this fact. So if B is the winner and I'm raising A, then either B will keep winning or A will win. Right? Okay. So B does not win here, but if B is at the top, then B is definitely going to win. Right? So what that means is there's going to be, if I just focus on, and so this is where I might take some liberty and not give you like the full details of the proof. Even though it's a simple proof of the theorem, is still quite long, and it's got many cases. So I might skip like 1 or 2 steps which are not particularly informative. This one I wanted to do because it shows that even for some fairly obvious things like this, you need to invoke strategy proofness and unanimity. So something as simple as this, you have to invoke both unanimity and strategy proofness. Right? Okay. So because B does not win when it's at the bottom, B definitely wins when it's at the top, which means that if I just look at rankings of this type, the first J people rank B at the top, and the next n minus j people all rank B at the bottom. Okay. Then there'll be some j, there'll be a smallest j for which B becomes the winner. Does it make sense? Okay. With j equal to 0, B is not the winner. With j equal to n, B is definitely the winner. Therefore, there will be some first j for which B becomes the winner. Okay. And that's what we're going to call R. So this R, the first time where B becomes a winner is what you can call the pivotal voter for B. Yeah. Okay. And in fact, the exact statement of this step is a little bit stronger. I'm going to make this exact statement, but I'm not going to prove it. Okay? So the exact statement is that of step 1 is that there exists R such that if the first R voters rate B first, then B wins, regardless of what anyone else is doing. Okay? R could be N, yeah. It could require unanimity for B to win, yes. Okay? And R could also be 1, where if the first voter says yes, then it wins. So there exists R if the first R voters rate B first, then B wins, and no, B is not. So this in this election, voters and candidates are different. The question was, does this include B itself? So there's something called committee election, where voters in a committee are choosing their chairman, or chairperson, or chairwoman, right? And so those elections are more complex. But here, the voters and candidates are different people. So, yeah. So the first R voters rate B first, then B wins. But this result is general enough. Let me put it this way. This result is general enough to also encompass the case when the voters and the candidates are themselves. Okay? So we didn't assume that the voters and the candidates are different. We also didn't assume that the voters and the candidates are the same. So if the first R voters rate B first, then B wins. If last N minus R plus 1 voters rate B last, then B does not win. Okay. And so the proof just follows, if you just take this first R and then you keep applying this factoid again and again, you basically get this result. It doesn't really matter how you're rating other people. Okay. So if the first R voters rate B first, then B wins. If the last N minus R plus 1 voters rate B last, then B does not win, regardless of what does or does not happen. Yes? So the question is R independent of the complete rankings? Yes, but R depends on the voting rule, on the social choice function F. Yeah. And R could depend on B. So you can think of R as being a function of the voting rule itself and of the pivotal voter B. And so that's basically what we are saying, that as long as the first R voters rate B first, it doesn't matter what the rest of the rankings are, B is going to win. As long as the last N minus R plus 1 voters rank B last, B is not going to win. And it's basically you just take this first time which wins and you basically apply that factoid again and again, that if switching things out here could have made a difference, then you would violate strategy proofness. Or if switching things out here could have made a difference, then you would violate strategy proofness. No, we have said a lot, because so the question is, what have we said? What we have said is that it doesn't matter what the remaining rankings are. It's not at all obvious that this pivotal voter, this kind of R has to exist. Okay? But I'm saying the first R voters rate B first, then B wins, regardless of what the rest of the rankings of the first R voters are. And when the last N minus R plus 1 voters rate B last, then B does not win, regardless of what else is happening. It's a non-trivial statement that you would have to prove, right? So you would have to first, like for example, this assumption that we had, that if B is last, then B does not win. No, R equal to N. Oh, you're saying that R equal to N would be trivial. No, sorry, because I couldn't have, go ahead. Yeah. The second statement may not be true with r equal to n. No, it's last n minus r plus 1. So if we said r equal to n, then this may not be true because, yeah. So it's a non-trivial statement. It's just not hard to prove once you have this by doing this factor repeatedly. Okay. So the second step. Okay. So there's on the email, the syllabus that we sent out, the full paper is there, right? So you can always go and look. And unfortunately, the thing is that some of these steps are very intuitive and they give insight. Some of them are just like case analysis. So I might not give a proof of this this step, at least not a full proof. So what this second step says is that so remember, R is the pivotal voter for B. Okay. If R rates K first, then either K wins or B wins. This is like almost like half a dictatorship. Okay. So you take this pivotal voter for B, and this pivotal voter for B, if the pivotal voter rates K first, then either K wins or B wins. Okay. So and then I'm going to also write down step 3, and I'm going to poll the audience whether they want to see a proof of step 2 or step 3 or neither. Yes, go ahead. The question is, well, R is the pivotal voter, so if R rates K first, then only K will win. No, because this step only applies in a very specific situation. So R might rank K first, but maybe the remaining guys don't rank B last, right? Yeah, so step 1 is incredibly narrow. It only applies in this very narrow sense where either the first R people all rate B first, or the last n minus R plus 1 all rate B last. Okay. And so it's possible that R rates K first, but we are in neither of these two situations. So it's possible that B might win, or it's possible that K might win. But that's basically what you're arguing is basically the steps in the proof. You would start from, if R rates K first, then you would start from this situation, and you will gradually sort of raise B, and you will get some kind of like a proof. Okay. And then in step 3, is that the pivotal voter. So in particular, I feel like the most informative part of this proof is actually the simplest one, where if you show that B is last, then B cannot win, because that's the one that really shows you how you're going to use unanimity and strategy proofness to argue about how things change. Okay, the other things are all basically the same kind of case analysis applied again and again and over again. Step 3 is that the pivotal voter for any two candidates is the same. Okay. So, and my claim is, as soon as I show that the pivotal voter for any two candidates is the same, then I'm done. Can someone point out why I'm done? There's one more assumption that I should have made, which I didn't make. I have to assume that there are at least 3 candidates. So Gibbert's other way to apply, you have to have at least 3 candidates in the election. If you have only 2 candidates, then you can essentially do plurality, majority, and majority is strategy proof. So can someone, like, if I have step 2 and step 3, then can someone sort of complete the proof of this? Or Yeah, so R becomes the pivotal voter for K as well, but that doesn't necessarily lead to a contradiction. Or doesn't prove dictatorship. Yeah. So let's also see. So let's say let's think of three things: K, B, and C. Okay, let's say they're all different. Oh yeah, yes, R becomes the dictator. Sorry. And so the reason R becomes the dictator is because R is pivotal for both B and C. If R rates K first, then either K wins or B wins, but also either K wins or C wins. But B and C are distinct, right? And so K has to win. So I know I'm like tilting the outcome in a decision that I like by repeatedly saying that the proof is just case analyses. But does someone want to see a proof of step? Should I do a proof of step 2 or step 3, or should I move on? Okay. It's basically the same ideas applied again and over again. Even if you see the proof, because the cases are so long, it'll be hard to remember without going back and referring to the proof again. Really, the best way of remembering this is these 3 steps. Okay. The first step shows that there's a notion of a pivotal voter. The second one shows that the pivotal voter is a half dictator. And the third one claims that the pivotal voter is the same for everybody. And so if there are at least 3 candidates, then the pivotal voter is actually a full dictator. So now, of course, I mean, step 2 is sort of, if there are only 2 candidates, then step 2 is backwards. There's just 2 candidates, so one wins or the other wins. They could be doing anything. It doesn't matter what they do. So if the first R voters rate B first, then B wins. But there's nothing in this step which claims that the first R voters don't rate B first, then B does not win. So they could be doing whatever they want. Right? So because if R rates B first, then we are definitely not in this situation. Right? We may or may not be in this situation, we're definitely not in this situation. There's no contradiction with B winning. So this is sort of one of the strongest indictments of sort of how democratic processes work, and this is the way, yeah. Yeah. So the question is, can you apply this rule recursively?
Yeah, probably, but does it imply that so whatever the ranking of the dictator is the outcome?
No, not necessarily. Okay. The question is the ranking of the dictator necessarily the outcome? No. For rankings, what you can do is you can choose one dictator for position 1. Then you can say assign somebody else to the dictator for position 2. Okay. Because I'm the dictator for position 1, there's never any incentive for me to lie. At least if you want weak strategy proofness, which is all we are shooting for. Yes, go ahead. Sorry? Yeah, so if you, so the question is what happens if you do something at random? You mean the social choice rule does something at random, or if my proof had done something at random? But who's you? I mean the proof, I mean the actual F, or just in the proof technique? Yeah, so I think this only applies for deterministic rules. Randomized dictatorship is also a, yeah. 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 It would be, yes, so the question is what would happen in this proof if we change the ordering? Yeah, it would just, if the voter number 5 is the pivotal voter, if we were to reorder, so voter 5 becomes voter 2, then voter 2 would become the pivotal voter. And that is because we know that the rule is, we assume the rule is unanimous and strategy proof. We prove that there's a dictator. And so no matter how you reorder, wherever the dictator is where the pivotal voter will end up being. Because basically what this says is if the first R voters are rating B first and R is the dictator, then of course it's going to win. If they're voting B last and R is the dictator, then of course it's going to lose. So I'm out of time, or I think I'm out of time. I think I'm out of time. So I'm going to stop in 2 minutes. So this basically sort of shows that you can't do anything. But in fact, in the next lecture, we're going to see many, many examples of very strong theorems where you actually can get strategy proofs. Okay? And so it's important to understand, it's important to sort of understand the exact assumptions that we are making here and see which assumptions can we push and which assumptions can we not push. Okay? And in particular, there's something that someone said which is going to be an important, which is going to be the most important thing that's going to help us get to the right, get to positive results. And someone said, can we not assume that people have utilities for these, that voters have utilities for each candidate, okay? And you want to maximize the overall utility or something, right? And that itself won't really help because the result is very strong. But if you, just having a utility function, just saying that people have utilities for candidates is just too general. It won't really help because utilities and rankings are completely consistent with each other. But what would really help is if you could claim that, if you could assume that these utilities come from a model. So instead of saying that people have general utilities, for example, you could say that voters lie on a left to right spectrum, okay? And candidates lie on a left to right spectrum. Okay? And a voter, so this is a voter, this is a candidate, and the voter's utility for this candidate is just the negative of the distance between the two. I want a candidate whose views are as close to mine, and my views also lie on a line, and the candidate's views also lie on a line. Okay? You could assume that voters' utilities are 0, 1. A voter has a utility of 0 for a candidate or 1 for a candidate. Okay? And then you could ask voters to just report all the candidates for which they have utility 1. Okay? That's called approval voting. Or you could assume that you're doing some kind of a complex election where people have, there are many, many budgets. And what people want is their ideal budget, and they only want the stuff that's in their ideal budget. They don't really want anything outside it. Okay? So basically, when utility looks like a step function, it looks like a line. And we're going to later see some situations where the utilities lie on a median space. Okay? So in each of these situations, we are going to obtain a strong strategy proof results. Okay? So I think that's going to be the next lecture. Thank you.